Hello again, folks. Today we'll be covering section 6-7, exponential and logarithmic models. Here's a quick view of the calendar. Okay. This video is for Monday, June 13th. Hopefully not Friday, right? So we'll be covering section 6-7. Just kidding. The packet that I have for you today is just like 2 or 3 pages, but there's an overview that I made. These are the different graphs that you would see depending upon the incarnation of the exponential or logarithmic model. They're pretty neat, actually. I'll try to give some examples of each. Go through that in a moment. Then there's a word problem about carbon dating, which to me was the most interesting. So I wanted to go through this with you. And I tried to make a diagram to explain exactly how this process actually works. So I drew some simple, it's not really a schematic per se, but the thought process to describe the transmutation of carbon into basically nitrogen. Then there's a population growth problem. How you would fit the pieces into the model, and what you could use your calculator for to accomplish the same. Okay, so if you're following along, do print that out, and I'll try to annotate. Let me move this out of the way and turn on the projector. Let's see. Very good. We're gonna adjust the camera here. Alright. Let's see if that's bright enough. Yeah, somewhat. Okay. Looks a little crooked. See if I can get it to persuade us. There we go. Okay. As I said, this is an overview. Sorry to walk in front there. Of different models for nonlinear behavior. Or at least something that has this curve like that. Let's see. Some more position. Solve right. Alright. Primarily what we're interested in is exponential growth, because I have a population problem, and exponential decay, which is for the mass of a radioactive substance over time. I think those personally are the most interesting. But these other things exist. Right? Unrestricted population growth would probably be simulated by this model of an exponential function or equation. Right? The mass of a radioactive substance would be modeled by a curve downward, right? It would diminish over time, right? Then there are these other things, which are also interesting. I shouldn't be moving that, okay? Logistical growth, right? This is interesting because although it's still based upon an exponential function somehow, it has something of a cube root sort of shape to it. If my memory is correct. Anyhow, this curve is known as a sigmoidal curve. And it's interesting also because it has 2 asymptotes that are horizontal between the y-axis and wherever the ceiling of this is. All right, an example of something that would best be modeled by this function would be a bacterial culture. All right, in which case the conditions are ideal, at least initially, and then less favorably. Right. Sort of feeding bacteria and giving them the proper amount of probably water and or light, and then suddenly not. Science is very cruel, as you know. Anyhow, this is a more famous incarnation of an exponential curve known as the Gaussian or bell curve. It could be modeled by this. If you type this into your calculator, you can get it to make this cool sort of bell shape. All right. In the case of test scores, in this scenario, they would be, normally we have a range of 0 to 100, but you can, if you wanted to, shift the bell curve so that the average, rather than aligning with 50, aligns with 0, and then in that case there'll be a negative end and a positive end of it. Then there's logarithmic growth, based upon the natural log, right? So base e, or common log, which would be base 10, right? As you can see, they're very similar, right? They're both arcing like so, as logarithms do. But in this instance, it's meant to be a little bit steeper, perhaps, and therefore the growth is a little bit faster. Whereas in the case of a common log, it's a little bit flatter, right, and therefore a little bit slower, right, in terms of the y value. Okay, I'm going to give you examples to this type and this type because I think they're probably the easiest and probably the most interesting. Not to corrupt your opinion, but just to get your feet wet. Right. With that in mind, let me show you a word problem that I've prepared. And I broke it up the way that you will see, which might be considered a little unusual on purpose. Right. Here's the whole thing, and obviously you can't read that from far away. Let me get this out of the way. But I wrote this in a sort of an odd way. When you, not that you necessarily will have this job, but if you were teaching somebody else something, my feeling is that you should use a lot of color, which is why I do that, to emphasize different things or things that are related somehow, they'll be the same color. And then, rather than write things in the standard block sort of indentation that we have, maybe put things in the center and then space the pacing, what would be separated by commas or periods even, by separate lines. Right? That's why I did that. I really want you to hang, on certain words in order to really grasp what is going on here. So let me, if you'll humor me, I'll read this to you in the way that I've intended it. All right. This is about carbon dating, right? Which is a fascinating subject. All right. When an organism dies, the total amount of carbon-12, right, that is the stable non-radioactive carbon atoms in the substance, or in the organism in this case, in its body, remains fixed. If it's not radioactive, it's not going to transmutate into something else, right? While the total amount of carbon-14, that is naturally radioactive carbon that coincides with carbon-12 in the same organism, continues to decay over time without replenishment from a source of food or the air, right? Or if it's an organism that lives in the water, perhaps. This is how we date things. Normally, that are very old. Normally, when alive, right? That sounds silly, right? The ratio of the amount of carbon-14 to the amount of carbon-12 is 1 to 10 to the 12th. That's 1 to a trillion, right? A trillion being something like this, 12 zeros, right? 0, 0, 0, comma, 0, 0, 0, comma, 0, 0, 0, comma, 0, 0, 0, 1. All right? 1 trillion. At least in the United States, that's the way that we have the nomenclature. All right? This is up to 100. That's 100 million. 100,000, 100 million, 100 billion. Then we, in the United States, we have a trillion at this point. All right? So, to estimate the age of a fossil, the scientists use a formula based upon exponential decay, which is, again, one of these things from the models that we have listed, specifically this one, all right? Some version of this. It isn't going to be exactly the same. More than likely, the labels will be changed. But for something that is diminishing over time, curving down, we would use this. All right. So keep that in mind. And basically, compare what is the state of the ratio of carbons to what should be, all right? I.e. the fossil's ratio of carbons to the amount that is expected or normal, all right? Specifically, they use this incarnation of the exponential decay function. Right? So let me zoom up a little bit, or scroll up a bit here. Take a look at this for a moment. Okay? Get that out of the way. 3, 6, 9, 12, yep. Okay. Here you have an exponential decay, notice the negative here, all right? And this would be the A value that's sitting in the front, all right? This would be the input value that we normally would think of as being X, but in this case it's T for time, all right? And a rate of change that is attached to it. Anyhow, this is a function of time as opposed to a function of x, and if you wanted to, you could call this r of t as opposed to y of x, you know, something like that. Right? Let me back it off a bit. All right. Now the real question is to estimate the age of a newly discovered fossil for which the ratio of carbon-14 to carbon-12 is the R value here, 1 over 10 to the 13th. That's 1 to 10 trillion as opposed to 1 trillion. All right, so significantly less. All right. Here again is the starting ratio, and what we're going to input eventually here is what it becomes. Right? So the way that this is rigged, all right, if you can solve for t, you could figure out the amount of time that it would take to get from here to there. I tried to break it up into these 4 steps more or less. All right, you would identify the appropriate model. All right, let me show you that and we'll get through it. All right, I'm gonna get some gobbledygook out of the way here. All right, I need a little bit of light, so okay. To stick with this sort of process here, we'll compare it to the. I keep putting this away somewhat foolishly. Compare this, what is given here, to the appropriate model, which in this case would be exponential decay, to give away the store, but so here's how it would look. The model that we're using is exponential decay. All right. So some similarities to this. It's the same basic shape. A little tweaked in terms of the labels. Okay? So identify the appropriate model and then compare the model to the given formula to translate what the variables would be. This is what the model is. I'm going to write it immediately underneath it for the sake of comparison. So here is the thing, R, where there would be a Y. Right? This ratio of 1 to a trillion. There's E, good old E, base E in this case. And then negative T over 8,223. All right, now just to compare and contrast, which would be to point out what is dissimilar. I'm going to circle these things. Remember, A is the start, all right, the starting point, all right, more or less on your graph. So because we're dealing with exponentials, a base here, and the actual input value is as an exponent, all right, this is the start. So what is sitting in that void, or that place, would be the ratio of 1 carbon-14, all right, to a trillion carbon-12s. Right? That's the normal situation. Right? When something is alive. Right? In terms of a function, a graph, that would be the location of, you put a 0 in place of time, right, which would be standing for x. You would have that value as your start on the graph. 0, 1 over 10 to the 12th. Right. You're still having this function that's arcing downward like this, right? But that's the y-intercept starting point. Okay, the bases are e in this case rather than some other number. Negative implies that it's a decay down rather than curving up. All right, and the actual input value, notice, is this. I'm going to put a line here as if this was a fraction. All right, the input is really x, is really t in this case. This is the input variable. All right, t for time since apparent death. Not to be grim. All right. Time years. All right, since something died, because if it died, then it is presumably not breathing, all right, not eating. Dead people don't eat, right? Or organisms don't eat, right? I mean, I suppose there is maybe some superficial amount of fluid transfer, but it's not quite the same thing, all right? Anyhow, this other value that is here, all right, I'm going to try to circle in maybe a different color. I'll try. I hate to use green and adjacent to red, but please forgive me. I want you to think of this b value here, all right, as it's a number that's multiplied by the input value. But the way that this is prepared is basically a ratio in and of itself. It's a fraction. So I mean, like, if you were to take this and split it apart, you would see this. It's very faint. You would see t times 1 over 8,223, all right, and a negative here, all right. This is what the b value is. All right. That's b. All right. All right. Essentially, this is a rate of change, because it's in the style of a fraction as it is. It's rather than, like, a lot of times when we do financial things, right, normally the rate of change that's quoted to us is a percentage, which can be converted to a decimal or it can be converted to a fraction, but it's already given to you as a fraction. All right. Without doing it a grave injustice, let me just tell you this much. This is something that I believe is known as the mean life as opposed to the half-life. It's based upon half-life. All right, you can calculate it from that, but it's actually mean life. The actual half-life, which is denoted by the lambda symbol, for something like carbon-14, would be, I believe, 5,700 years, something like that. Right? The mean life would be that figure times 1.443. And that's how you get this figure of 8,223. Right. Anyhow, don't dwell upon it for right now. Let's just think about it as math people and go, it's a rate of change, right? It is necessary to simulate the conditions that are described, right? All right, but just so you understand, this fraction is what would be standing in place of the b, not the x per se, because the x value is really time, right? That's the input. Now, just to give you a feel, all right, I'm going to come back to this. What is physically going on, because that actually is really fascinating. I made this other diagram. Actually, it's in the same book here, so let me just scroll downward. There we go. All right. No, I don't want that. All right, if you look at the second page here, this is the actual process, all right, with some labels. Get that out of the Way. All right, stable carbon, as it is written in a textbook, would be like this. All right, here's the symbol for carbon, C, capital C. The number of protons and neutrons would be the number sitting on top. This is alternatively known as the mass number. All right. Of an individual carbon-12 atom. All right. Okay. This perhaps more famously what is exclusively the number of protons. This is known as the atomic number. There is another thing that sounds very similar, which is atomic mass. And if my memory serves me, atomic mass is more or less an average of all atoms of carbon, which is a lot of times where you see a decimal in a textbook rather than a whole number like 12. Because it can vary, right? We have carbon-12 atoms, say, for example, and there's carbon-14 certainly, and maybe even carbon-13s. All right. Anyhow, during the radioactive decay process, all right, this is to summarize. The number would start with 14, right? The mass number would start with 14. Why? Because in that case, there's more neutrons than normal, right? Extra neutrons, if you will. Right? It's exactly like under stable conditions, it's exactly 6 and 6, right, for carbon-12. But for carbon-14, all right, the mass number is 14, which means that there are 8 as opposed to 6 neutrons, right? I was suspicious of my spelling. All right, now this is a naturally radioactive process, right? And it's in, of the radioactive processes. This is the beta type. This is known as the beta decay. Basically, what happens is, and this is the part that I find just incredible, a neutron turns into a proton, all right? And in the process, that is, it goes from being electrically neutral, all right, as neutrons are, and becomes a proton basically by forfeiting, for lack of a better phrase, its electron, right? All right, so if you are a proton, basically that would be a positive naturally, and if you then give up an electron, all right, you are no longer electrically neutral. All right, there is another subatomic particle known as an electron antineutrino. That's what this is. But just realize this in a nutshell. This is the most integral chunk of what's going on here. You have a neutron turning into a proton. All right. So what ends up happening is this. If you suddenly have more protons than you had before, because you went from 6 to 7, this is again the atomic number. Remember that the atomic number is what identifies the element. All right. Well, you're no longer carbon. All right, what are you? Next element on the periodic table is nitrogen. Right? And it has still the same number of the mass number, because even if one thing changed into another type, they are still part of the same nucleus. Right? At least what's left over. And this becomes stable nitrogen. So isn't that interesting, right? All right. During the radioactive process of beta decay for a carbon-14, it just is turning into nitrogen. Right? It's turning into a gas. Right? A solid is turning into a gas somehow via radioactive decay. Right? Anyhow, getting back to this, the other parts of our conversation here. I'm going to substitute and solve, and when it is imperative to do so, you employ natural log as a technique, all right? And then I'll show you a graphical method for finding the same information. I'm going to write this over here and then turn off my projector. So we have this, r is equal to 1 over 10 to the 12th times e, negative t, 8,223. All right. So if we substitute the value for r given, which is 1 over 10 to the 13th, 1 to 10 trillion, where would we put it? Here, on the left side of the equal sign. All right? So what you end up with then is this. 1 over 10 to the 13th would be equal to the ratio of 1 over 10 to the 12th times e to the negative t over 8,223. Again, this number 8,223 is dependent upon the element. All right, so like you could, how this was determined was via the process of calculating half-life. But again, I genuinely believe that is a mean life as opposed to a half-life. At least the number 8,223. Half-life is how long it would take for half of the unstable nuclei to change. Mean would be the average, all right, time it would take for all of the nuclei to stabilize. That is the radioactive nuclei anyway. All right, so the difference between half-life and mean life, if in fact I am correct when I say that, mean would be that one is the half amount of a time and this is an average amount of time. Anyhow, what we're trying to do ultimately is solve for t because we want to know how long, all right? So we're going to compare what would be normal to what actually is here, all right? And we have to rearrange this eventually to get it down to just t being on the normal tier, all right, of an equation, all right? There's a little bit of dressing up that we have to do, all right? First of all, we would want to pull the trick that we normally do, which is to isolate the base, all right? In this case, it happens to be base e, all right? When we then have it isolated, and that hasn't occurred yet, we can apply natural log because it is an inverse as a sort of cancellation effect, all right? It simulates something like that. Now, what would it take to get this to be alone on one side of equals? We would have to move this ugly coefficient, all right? There's a couple of ways you can do that, all right? If it's a fraction, and it is, all right? How do you move a fraction from one side to another over equals? Via opposite operations. If in theory it's being multiplied, that would mean that you divide. But when you divide fractions, what ends up happening, spitefully, is that you end up multiplying anyway, by the reciprocal. For the lack of space, what I'm going to do is I'm just going to write in black, sort of superimposed upon things. So I would have 10 to the 12th over here, and remember, your hands are tied. If you've done it here to justify this process, make sure that you do it over here as well. So times 10 to the 12th over 1. There would be, strategically so, a cancellation effect. All right, that leaves you with just e on one side, and these interesting guts here, 8,223. And there's some straightening up that has to occur here. All right. Now, if you merge these ratios together, what you would get is 10 to the 12th above the line and 10 to the 13th below the line. All right. As a math-oriented person, all right, remember when you have the same bases, you can employ the quotient rule of exponents, which would say there's an abbreviation for this. All right. We could use the quotient rule for exponents which says that when you have the same bases, you can subtract these, right, in the intuitive way. 12 minus 13, right? Whatever you get as an outcome, write it above the line. So whether it's negative or positive as an outcome, that is in terms of the degree, the exponent, just write it on top. 12, essentially, minus 13 would give you 10 to the negative 1. And then this is still over here, e to the negative t over 8,223. Okay? Right, now, at this point, we could apply the inverse, the natural log. All right, remember, a natural log, alternatively, instead of natural log of x, that's the equivalent of saying log base e of x. All right, it's just a sort of an abbreviation unto itself. All right, if you apply the natural log here, legally speaking, all right, then you're obligated to do it here. We wanted really to do it here anyway. All right. All right. I need a little bit of space, so I'm going to erase just what's above here. And show you the outcome. All right. In this case, we're going to leave it alone for the moment. I'm just going to take advantage of the situation. I know that when I have an exponent attached to the guts in here, if it suits me, I could write it on the outside, and legally it's the same thing. All right. Essentially, I want to do the same thing here. All right. May not be necessary, but for the sake of clarity, I'm going to do that. Okay. When you take the, basically embed a function in its inverse, what happens? There's more or less a cancellation effect in terms of equations. What ends up happening is that if it was just an ordinary function of x embedded in, say, the inverse function, you would get x coming out as, the outside. Now, the nature of an exponential function is that the input value is written as an exponent anyhow. Right? At this point, what I would do, just because I feel more comfortable, is I would take advantage of the power rule of logarithms and just do what I'm allowed legally to do, which is to park this here. Right? That may be overkill, but it is correct. Right? This, just unto itself, is the value of 1. Right? Okay? As I said, it's something kind of like a cancellation effect, you can think of it, right? It's going to be negative t over 8,223 times 1, essentially, which is superfluous. You don't even have to write that, all right? Meanwhile, over here, a similar effect, all right? You'd have negative 1 times, as a coefficient, all right, the natural log of 10, okay? Now a little bit of more rearranging, right? Couple of things. I'm going to get rid of that because, as I said, it's superficial. If you want to get rid of the negatives here and here, how so? By dividing each side by a negative. There's a 1, you can think of that 1 over here. And then you have this. The natural log of 10 is equal to t over 8,223. And now the last step would be to move this denominator because the variable is in the appropriate place. It's more or less on the usual tier, the normal level for a variable to be when we're solving for that variable. So perform opposite operations here to move it from one side of equals to the other. If this is being divided by 8,223, then multiply by 8,223 here, is more or less above the line. There's a cancellation effect. If you've done it here, you're obligated to do it here. Okay? So that means, and I like it better in the orientation of the letter in front, t, the amount of time that we were looking for to have transpired since something apparently died, would be 8,223 years, all right, times the natural log of 10. All right, now what does that mean? Now if you take a calculator, we'll figure it out, all right? The average amount of time for the carbon-14 to stabilize, essentially, if in fact that is mean, and I'm fairly certain that it is mean life as opposed to half-life, 8223 times the natural log of 10 gives you 18,934 years, give or take a little. All right, so pretty interesting. Save that number. All right. This is about 18,934 years since death. All right. When the organism died, it was no longer replenishing its carbon-14, its radioactive carbon-14. Okay? So that's neat, right? There's some limitations, I believe, on this. Like, I think they can only go back about 60,000 years ago or something like that. With carbon, at least. Might use some other substance. All right, now, remember, there's another way, especially if you're armed with a Texas Instrument calculator, a graphing calculator, to arrive at the same result. All right, let me show you that to remind you. That would be part 4 of the same question. If we were going to do this graphically, that is via TI 83 or 84. All right, this is neat. It's that same technique from, if you remember, solving quadratic equations, which is to more or less pretend that you have the two halves of your equation are y equals something, right? And then look for the point of intersection, right? That is it in a nutshell. Make each half of the equation y equals something, all right? Superimpose the graphs and look for the intersection. It's a neat trick, right? So if this was our original equation, R is equal to 1 over 10 to a trillion, 1 over a trillion, times e to the negative t over 8,223. Then what I'm getting at is that after the substitution has occurred, which is to replace R with 1 over 10 to 10 trillion, this first value here, first half of this equation, we'll call it y1, right, in the list of y things, all right? And this half of the equation we'll call y2, right? 1 is going to be the curve that we expect for exponential decay. The other, if you reason it through, and you have to trust yourself that you can talk yourself through it. This is ugly, all right, but what kind of thing is it really? It's a number. It happens to be a very puny decimal because it's 1 divided by 10 trillion, which is very, very small, all right? And for that reason, we may have to adjust the screen settings on our calculator. But this is just a regular number. And if it's just a regular number, what type of graph would that make? This is going to be a very low horizontal line, right? Because y equals a number is a horizontal line versus y equals something that is base e is going to be a curve. All right, in this case, a decay curve because it's negative. All right. So what we should anticipate is something like this, and then a horizontal line superimposed upon it. Somewhere there's going to be an intersection. And at that intersection will be the y value that is the year that we just calculated algebraically. So that's kind of cool, right? Again, because the numbers are so small, expect that you're probably going to have to tinker with the dimensions of the screen. Right? So let's do that. All right. We'll start with the number 1/10 trillion. You could do it a couple of different ways. Again, I like the fancy way, so I'm going to put this in the intuitive fraction-esque version of this, which is an obvious top over an obvious bottom. So 1/10. Yeah, I'm writing it backwards. Sorry. 10 to the 13th. All right. If you did /, just I would put it in a parentheses just to make it a little bit nicer and neater. This, if we were going to graph it by itself, again, remember this is extremely tiny. All right. It may not graph real easily. Let's see. I'm going to hit graph and just show you. I already been messing with this. So let me hit zoom. If I started with standard, and this is 10 by 10. All right, just slightly distorted because of the dimensions of the screen being wider this way rather than this way. You can't even see it, right? Because the first increment is 1, all right? Off the x-axis, it's just 1 up, all right? So you would have to zoom. So what you could do, and you may have to do it several times, you could hit this as a more brute force way of doing it, 2, and then hit enter, and you could, it's still not even showing up because it's so tiny, right? Because that increment is 1. Let's say you did it again. It may be possible if you keep hitting the enter, that you keep zooming in, that eventually you will get to it, but it's kind of, it's kind of a waste of time. So what you would do alternatively is go to zoom and then try zoom fit. Which is this option here. And there's an error message. Quit. Okay. It's so small that it might be a little hard for the calculator to handle, but I know that I've gotten it to work, so I'm going to be adamant. If you really, really have to, then what you will do instead is you will go through the manual. All right. Again, if you think of this like cars, all right, zoom is the automatic transmission and window is the manual transmission. You have greater control with the window, but it's a little bit more, you have to think about it a little bit more deeply. All right, so I'm going to try maybe a little bit stupidly one more time. I wonder what Z decimal would be. Curious, I never used that. Nope, still too tiny. All right. Zoom, I'm going to go back to standard first before I mess with it. And now I'm going to go into window and I'm going to mess with these features. All right. Basically, what is the X minimum and the X maximum? That is really less of a concern to me. If I have to, I will adjust that. But it's really the Y's, all right, that I need to adjust. Y on a curve like this is levels off at 0, right? There's the asymptote there. So there's no reason for us to have negative values for Y to begin with. So I'm going to just change this to 0. All right, and then for the maximum, what would be a reasonable one? What is normal? 1/10 to the 12th. All right, so that is again a puny decimal. All right, but this is even a punier, for lack of a better phrase, decimal. So that would be the tippy top, all right, of the range in which we are looking. So I'm going to use this, but I'll use it in the negative version. So I'm going to put 10 to the negative 12th as if I just wrote this in that notation. So 10 to the, I'm going to use a caret symbol here, and then use this button for negative. Import here, and then put 112. All right, I'm going to keep the scale the same, as I don't really want to think about it. Look, it adjusted it. That's 1 times 10 to the negative 12th, if you're wondering what that E stands for. And let's see if that is sufficient. If not, I will come back and tinker with this further. Yep, there it works. All right. Now this is really teeny. Like this, what's running along the edge of the screen here is the y equals 0. So that's the x-axis. We don't need to look underneath it anyhow. But as predicted, this is a very tiny horizontal, very low, I should say, horizontal line, right? The top of the screen up here, in theory, would be whatever the decimal equivalent of 1 over 10 to the 12th would be, right? I put it in the negative notation, but that's still the same value. A very small decimal would be the distance from here to there. But that's the ceiling, right? This is where the line actually would be because it's of 10 trillion, so negative 13. All right, now, I'm going to try to superimpose the same curve on this because I want to see a point of intersection. I'm going to go back to y equals and then enter some more values here. Well, first of all, I'm going to put in the equation, this half of it, all right, very carefully. All right, so I'm going to put in parentheses, even if it's a little silly, because I'd rather be safe than sorry. And I like the intuitive way of writing the fraction. So I'm going to put 1 over, I really could use negative notation too for the negative exponent. But this is intuitive, except that I can't write backwards. Come on. Sorry. 0, negative 12, there we go. Close parentheses. So that much is this half of the actual equation. Now I'm going to use base E. So you could put times, but it really wouldn't be necessary. E is over here. It's in blue, so you'd have to hit second and then natural log to get an E show up. And now remember, you have another situation where you have a ratio here, so you could do a couple of different things. I love this feature, so I'm just going to take advantage of it to death. And now, because I have a t here, and the calculator is rigged to be x, I'm just going to do what it represents really, which is negative x. So I'm going to put minus, and then x, and then underneath it, I believe the mean life, so 8223. Okay. And that should be fine. I mean, it does at least look the way it's supposed to look. All right, and we'll see if I can get away with just having set the manual controls to graph. Maybe not. I got to think about it. Oh, there's an issue. So I'm going to have to go back and tinker with it further. All right. So go back to window. And now as far as the x dimensions are concerned, all right, let's start with this. We really don't need the negative domain, so I'm going to start with 0 there. All right, as for the maximum of the x's, all right, this, just to sort of, again, trust yourself that you could talk yourself through it. If this is t, time, which is really x, that's the point that we're more or less looking for, all right? So something a little beyond that would be okay in terms of an x value, all right? That's why we're not seeing it, all right, on the screen, because it only goes up to 10, right? That's far short of, nearly 20,000 years. So what would be a reasonable value for x maximum? That is how wide the screen should be in this dimension. Maybe 20,000, right? If not 25, say. So I'm going to put 20,000, see if I can get away with that. All right, I'm going to leave the scale alone, and I didn't want to think about it. Now, let's test the theory. Graph. Here's the horizontal line. And here's the curve, yay, coming through. It's not really the most satisfying picture because it's right on the edge, all right? So let me do one more thing. I'm going to make this a little bit wider for the x value. So I'm going to go down here and say, let's do 25,000. Okay. Crosses, there we go. Very good. All right, now we could zoom, I suppose, but I don't want to mess with it. Let us get the calculator to now tell us what the point of intersection is, because the point of intersection is that year. All right, we'll incorporate coordinates that has 18,934 in it, or some decimal equivalent. All right, so if you go through second and then trace to get the calc feature engaged, notice that there is intersect. So choose option 5. All right, and it's going to ask you, is this the first curve? Which is, kind of a silly question because it's a flat line, but you go, yeah. All right, and then it moves up to the second actual curve, and you go, yeah. All right, and then you go, you want me to guess? And you go, yeah. All right, and there it tells you. All right, the x value where they cross, which is what we're really interested in, is 18,934 point, and change. Right. What is the y value at that point? It's the height of this horizontal line naturally above the x-axis, which is 10 to the negative 13th. That's 1e is the abbreviation that the calculator uses for times 1 times 10, right? It's the exponent that is negative 13. So that, all right? All right, because it would be in the orientation of a negative exponent would be up here, all right? So there you have it. This is a way to get the calculator to tell you the same information. Now, again, you have to have the endurance and the patience to tinker with the screen dimensions, but it's not impossible. All right. That's kind of cool, right? Certainly worthy of our time, I think. All right. Now, here's that other word problem. I'm going to turn this back on. There's more to it than that. There we go. No, I don't want to see that. No, I just want to see that one. Alright, this is being a pain in the neck, so I'm going to close that, open it again, see if I can get to where I want to be, which is right there. Now zoom. No. It wants to show me 2 pages at once. It's not something I want. Try again. It's very annoying sometimes. Alright, I'm going to do this the stupid way, but it will work. Yes, sometimes the stupid way works. Okay, this is similar, but it's for a population growth as opposed to a radioactive decay. So do expect at least this much, right? And I'll adjust the light here. All right. Humor me, I'm going to read this to you. The population growth. Sometimes the exponential model needed is given, as in the last problem, all right? And indeed, sometimes you have to find it yourself, all right? So if you have some idea, all right, of your choices, at least, and these would be the, say, 1, 2, 3, 4, 5, top 6, especially these two, as to what the shape would be. All right, you could borrow the model and then adapt it, fine-tune it to the problem at hand. All right. In this case, this will be for population. Now, how would you know that it's for population? Well, they might have that signal phrase there. All right. A population of fruit flies increases according to the model of exponential growth. All right. After 2 days, there are 100 flies, and after 4 days, there are 300 flies. All right. It's non-linear sort of behavior between x and y. All right, it would seem. All right, because if it was linear, it would probably be a little bit closer in terms of the magnitudes of the numbers, right? Certainly not 1, 2 to 100, right? And 4 to 300, right? How many flies will there be after 5 days? Is ultimately what you'll do. That's ultimately what you're going to answer, all right, or figure out, all right? But you need to adapt the model first. So here's this process. You're going to identify the appropriate model. I already kind of spoiled it. Exponential growth, all right, and its population. So we have this to begin with. A times e to the b to the x, all right, model. All right. Population growth. And now we're going to compare the model to the description to translate the variables. All right. What does that mean? It means instead of x, all right, you might use a different letter, all right, up front. I mean, it's not imperative, but let me put this here. Y equals, I'm going to leave A for right now, E, and I'll leave B for right now. But this is time, right? So it's days. So you might put a D or you might put a T if you'd like, all right? That's not visible. So days, essentially. So keep it X if you like, X's, all right? Or change it to D or T, whatever you would make sense to you, all right? What does it spit out, all right? What is the end of this machine here if instead of X and Y we call it days and something else? It spits out flies, right? It's gross, right? All right, with all due respect to the flies themselves. This is so many flies is what this thing is going to produce as a function of days. Okay? Now here's a little table under here to help you sort of walk through the process too. All right? The machine spits out flies. All right. So the input under normal circumstances, especially in the model, right, is an x value. In the context of the problem, though, all right, as I already mentioned, this is days. X input is days. All right, so many days. And Y's input is so many flies. All right. And then there's some data that is quoted to you, all right? So think of this as being x1, y1, x2, y2. Right? It's not a lot of data, but it's the best that you have to go with. All right. I'm going to scoot this down just to point at it. All right. Here's the data. 2 days, 100 flies. All right. 4 days, 300 flies. So 2 and 100. 4 and 300 is what you would put here and here. For reference, two days, there's 100 flies. On 4 days, there's 300 flies. That would seem to be very nonlinear behavior. All right, now, based upon that data, all right, there's 2 ways that you can go about this process. I'm going to do it the algebraic way because that is something that should always work 100% of the time. All right, if in theory you feel comfortable. All right, and the more you do it, the more comfortable you get. So let me show you how to do that. I don't like this in the way. Sorry, being anal retentive right now. We're going to figure out what is missing. All right. E is going to stay right there, all right? Because we already know that from the model that that's integral to it, all right? But we don't know A, and we don't know B, all right? That's an input value that's depending upon an amount of time that we could just whatever we want we could stick in here, and that will result in a certain number of flies. But the 2 missing pieces of information is the A coefficient and the B coefficient. The second way to do this is to basically build up a list in the stat app of your calculator, and it will spit, as long as you know that it's exponential regression, it will give you those pieces of information, lickety split. All right. Anyhow, let's do it the more brute force way because you need to have some foundational practice. All right, we're going to substitute the first ordered pair into the model and then solve for A. We're going to get an algebraic expression from that. All right, so I'll put it over here to summarize. All right, step 3 is sub to calc A. Just know that it's going to be an algebraic expression. All right, not a nice warm fuzzy number. All right, and then we're going to sub to calc B, and we will get a number in that event. At least I believe my memory is correct. Yeah, I mean, it's not going to be a satisfying number, but you will get an actual number. All right. And then you're going to put both of them, all right, B into the A equation, sub B into A algebraic expression, right? And you'll figure out what A, this will give you an actual number as well. And then sub both into the model. That's essentially the process. All right. So for A, we're going to use these two numbers. For B, we're going to use these two numbers and the A expression that we got from these two. Okay. Let me turn this off because there's a lot of gobbledygook, so I'll just move it out of the way by removing it. And go through the process. Okay. I think I could lighten up a little bit here. So. Maybe leave that. Okay. So, this is our X and Y, and we're going to use these two first. All right. So, in place of Y, number of flies, I'm going to put the number 100. We're going to be looking for A. It's again going to be an algebraic expression to start with. E, the B value we're not sure of, but we know that the X value is 2. All right. So we have this much. All right. If we're going to solve for A, we're going to have to do a bit of rearranging actually first. So let's do that. All right. This one is not hard. It's just a little uncomfortable, at least for someone like myself, because I don't like having exponents like that as a denominator, but that's what you're going to end up with. All right, if you're solving for A, and again, I can't emphasize this enough, it's just going to be an algebraic expression initially, then that really would entail moving this entire chunk from here over equals. So just temporarily, we're going to divide by E, B2, technically. Something divided by itself would cancel, and to get away with it, we're going to do it to both sides, so we have E, B2. All right, that means that for now, A is this ugly expression. E to the 2B to make it maybe a little bit nicer. All right, save that. All right, now we're going to use these two values, 4 and 300, in the same model, all right, and we're going to stick that A value in there as well. All right. So to do the work adjacent, all right, I'll write this in green because it writes very faintly to begin with. Y equals A e to the bx. Right. And I'm going to put I'm sorry, I wrote this backwards. That's y. All right, this is x2, and that's y2. All right. So I'm going to put 300 here, and I'm going to put 4 here in place of x. All right. And in place of a, I have this horrid-looking expression here. So I have 100 over e to the 2b times e to the b4. Okay. All right. Now, there's a couple of things we can do. I'm going to try to group the a's together, right? Because then I can employ rules of exponents, and I'm going to move the 100 from here to the opposite side, right? So up front, what's going to happen to this stuff is I'm going to just sort of slide the parts around. So it'll be 100 over 1, right, times the e that was there. So e to the 4b, just to put that in front. And that's a b, I swear. Over, all right, e to the 2b, right? And now, if I want, I could start simplifying this and moving that algebraically. Maybe the simplification would be better to set as an example first. These are the same bases. So one thing that I can do is employ the quotient rule for exponents. Right, which means that if they're the same bases, you could abbreviate this by subtracting these. Right, they're like terms because they're both b, degree 1 technically. So 4b minus 2b would just reduce to positive 2b. That's cool, right? The end result, regardless of whether it would be negative or positive, you would always put on the top tier. So what you end up with, at least temporarily, is this. You have 300 still floating around over here. You still have 100. The 1 here that I put there is just to show you split as fractions. It's superfluous. Times e to ultimately 2b, right? Now I have an obvious coefficient times the base of e. I'm going to algebraically scoot this from here to here, which is via division. And that will reduce to just the number 3. I need a bit of space, so I'm going to move some stuff. So we have 3 on one side, and we have e to the 2b on the opposite side. If we want to solve for the variable b, all right, we're going to get an actual number, thankfully. We're going to have to apply an inverse, which is a natural log. All right? So if you apply the natural log to here, for this is somewhat of a cancellation effect, and you really must do it here. All right? That means that you're going to get the natural log of 3 on one side. That's a number. It's just whatever yucky number that is. All right? And the effect here, in tandem with perhaps the power rule, is that it would be inverses essentially more or less cancel one another in the context of an equation. So you have 2b, the exponent times 1. So it's just 2b here. All right? Now, again, you isolate the b by dividing, and then you have this. If you like, you could write b like so. You could either keep it as natural log of 3 over 2, or give it an obvious coefficient of a half. It's the same effect. Natural log of 3. This is not recognizable as a decimal, but it certainly would be. It's an actual number in this case. Right, so we have a b, and we have an a expression. So if we wanted to, now we could figure out what a is as an actual number. We're going to substitute into the a algebraic expression to get an actual value for a. So this junk is going in here. All right? And there'll be some cancellation effect, thankfully. All right, so this would be 100 on top. E to the 2 times what I'm substituting is a half times the natural log of 3. Right. And a couple of things. If you distribute this, it would just be 2 times a half, which would cancel, leaves you with 1, which means that the denominator would be e to the natural log of 3, right? Which is again an example of inverses. All right, which means that you're just going to end up with 3 as the bottom, basically. All right. Why inverses? Because remember, natural log is an abbreviation for this. Log base e of whatever the argument is. So what you have is e to the log of e is a base e. And now the effect is basically a cancellation effect. So what you have is this. A is going to be equal to 100 over the argument, whatever is in there, so 3, right? Which 100 divided by 3 is 33.3 repeating. Leave it in the fractional form because it preserves all of that without having to round. So we have an actual number for B and we have an actual number for A. All right, what we're going to do is now sub both of these back into the model that I erased. So here is the model. Y is equal to A times E to the BX. All right. We have the A value as 100 over 3. Leave it like that. And in place of B, we have this. All right. If you like, the natural 1/2 the natural log of 3. Right. Really squeaking it in there, sorry. All right, now if we wanted to, oh, sorry, I put it in the wrong place. All right, it goes in place of B, not X. All right, so 1/2 natural log of 3. And then there's the X that is actually the input that is there. Okay. You have everything at this point to answer the question of, well, how many flies are you going to have after 5 days? Put a 5 here. And then you could use a calculator at this point. All right. However, what you'll end up with if you insert 5 in here is that this is so many flies. Is that you're going to get something like about, because it's rounded, 520, right? Using 5 as the input. Right. Being that there's a natural log here, you could simplify this by tinkering with it a little bit. I'm just pondering. Okay. Let me show you what you could do with your calculator, and you could get it to give you the same information again. All right. All right. If you're going to get your calculator to basically produce this value and this value for you, the actual numbers, all right, you would have to create a list similar to the block that was on that handout. So let me show you that. Yeah, don't erase that. I want to save this. Just for the lack of space, I'm going to put a sort of little thought cloud here. All right, if you're using a Texas Instrument calculator, which is cool, you're going to basically create a list of X's and Y's. All right, by going through the stat button. All right, I would do this. The lists that you see there, you may have to clear them. All right, L1 will be the X's and L2 will be the Y's. All right. Then you're going to go basically identify the type of model that we're following. So if you create your list, you're going to get it to give you the parts basically. All right. If you go through stat and then go over through calc instead of number, instead of edit. If you go down the list, you're going to choose exponential regression. Right, and it's going to give you this value and this value. It might have a simplified version of it though. All right, so let's do that first. So let me clear out my junk in here. All right. If you need to, get rid of some entries. Maybe do this first. If you hit second and then plus for the mem feature, you could clear all lists, clear all entries. I'm going to do 4. All right, and now it should be fine. If you go into stat directly and choose the first option 1, you'll have blank lists. All right, now again, I would make the list number 1 the x's essentially, and list number 2 the y's. We don't have a lot of data. We have just the information that is on day 2 there's 100 flies, and on day 4 we have 300 flies. So don't be a dodo like me and just call them the same thing. 2 is the first x, 4 is the second x, right? Enter. Now what would be concurrent with 2 would be 100. And what would be paired with 4 would be 300. Okay, that's as limited an amount of data as we have, but it's enough, at least to get to that. These values of A and B respectively. Right. So if you hit stat again and then scroll over to calc and then go down the list, you'll see exponential regression. That's for modeling things that you believe are exponential. So I'm going to go down to 0 here. Maybe if I can just hit 0. You can tell it to choose L1 and L2. In that respect, it's not necessary now, but if you had other lists that were filled in, all right, there's a way to tell it that. See in blue here it says L1 and L2. You could hit second L1, comma, second L2 if you needed to. But since there isn't any other information, it's going to assume first one is X and second one is Y. All right, and then it will spit out the information. Now, what do you get? Here's the model, A times B to the X, right? B is the base in this presentation here, and it's not really dressing up any other coefficient, right? What it did, actually, is it simplified the formula a little bit, all right? It concluded that, based upon the information, that this is, the B value is, in effect, similar to, if you recognize this decimal, the square root of 3, all right? If you recognize this decimal, that's 100 divided by 3, all right? So it's giving you all the same information, but it's giving it to you in a slightly funky way. All right, let me write it here just for reference. All right. They reduced it to this model. The calculator. 33.3 repeating, which is that value for sure. All right. And then instead of using E, all right, it concluded that you can get away with using this as the base. All right, 1.732 is the square root of 3. All right. All right. That means that if I were to clean up this portion of this, I should be able to get it to that, apparently. All right. I can't help but want to try. All right. So let me free up some space here. Okay. If you have this expression, e to the 1/2 of the natural log of 3 times x, all right? We could take advantage of properties of logarithms, all right? First of all right, instead of having a denominator, a fraction out in front as the coefficient, what we could do in theory is put this over here, right? According to the power rule, all right, and then it would be half. So this would be e to the natural log of 3 raised to the 1/2, right? And meanwhile, there's still this x here. .7, whatever it is what square root of 3 is. And you may notice immediately is that This is a half as an exponent, all right, which means it's the rational notation of a radical. Right? Remember, if you have an exponent that is a fraction, essentially, the denominator is the type of radical that it would be. So if it's denominator of 2, and it's being applied essentially to the gutsier of 3, that means that we still have this. We have e to the natural log of 2, 3 to the 1, and this is still an x here. All right. Nobody ever bothers to write the index in the case of a square root, but it would in fact be there. In the case of something that is a degree that is 1/3, in the cube root, you'd really have no choice just to distinguish it from the square root, right? But I like to put the index where it would be and the exponent essentially where it would be, all right? Now, this chunk of it is, these are inverses on top of everything else. And what happens when you have inverses is that essentially whatever the guts are in here, all right, they're going to be on more or less the usuals here, all right? So if I'm not even considering the x, I'm just kind of separating it here. What is in blue essentially would reduce this to the following. What is in blue would end up being the square root of 3, right? And since I didn't really bother to incorporate this x here, all right, it still would be an exponent. Like so. All right, you could, in theory, have maybe tried to pull some tricks, but it would be unnecessary. So what does that leave us with? Basically that. That's why they use square root of 3 instead. Okay, that seems to be legit. All right, now either way, I'm going to use just maybe the complicated version of this, and then I'll go back and use what the calculator assumes is true, and what seems to be true, and then arrive at the same value for 520 approximately for after 5 days worth of work. All right, so just to expedite doing that, let me go in here and type in what I have. And then I'll show you after the fact because it's easy to do it while looking at it. In the normal orientation. Here is a fancy way of having entered this in y equals. Okay. That's the a value. That would be 33.3 repeating if you did the actual division. I'd prefer the fraction just because it's preserving all of infinity if you write something that way. And here is just taking the coefficient of the natural log 1/2 and making it a denominator. Okay. The x is completely out of the picture here. It's just adjacent to it. All right, this is the coefficient that would be the letter b under normal circumstances, not the way the calculator thinks of b. All right, now I did mess with the screen dimensions, so what I probably should do is just put this to standard first, and then let it draw. All right, and we'll see. It's a little hard to see it. I'm gonna have to zoom out. All right, so 3. Still not satisfying. I'm gonna try zoom fit. 6 is not gonna show you where the point of crossing the y-axis is concerned, which is annoying. So I'm gonna go back in here. Let me see what the if you get this, it means it's crashing. So you may have to turn off your calculator and turn it back on after you've paid for your sins. All right. Here's the drawing. I'm gonna go. Come on. After that stops running there, I want to see what the dimension. It put them back in Z standard, so 10 by 10. I'm gonna try fit. No. Well, it's basically showing you the starting point. Like the x-axis would be well below the picture here. So there. All right, now, if you hit second and then trace, you could test, pardon me, graph. If you hit trace, you get the cursor where it's supposed to be. You see that the starting point is the A value, right? So it would be 33 up. That's beyond, positive 10 for the y. So, so it's up here instead. And if we want to see what the x value will be when it's 5, at this point we can enter 5, and it should spit out 219 and change. All right, so like previously rounded, it's about 520 flies. Yeah. Stupid. Trace. 519 again and change is about 520 flies, right? And it would be at this point on the graph. Okay. Now, if this is correct, and I believe it is, that could work out with the having taken care of this inverse situation here. You could actually replace it with the square root of 3. All right. So essentially, y is equal to 33.3 repeating times the square root of 3 with that as your x input there. All right. It's easier to type that naturally. So I'm going to type this first. I'll put 100 over 3 just to again preserve all of infinity. But instead of putting base e, I'm going to put the outcome of this. Square root of 3. And then outside of it, the x is the input. All right, so the condensed, compacted version of this. Okay, and then we'll see if in fact these are the same, and they are. The graph should just be undistinguishable before and after it draws both of them superimposed. So here's the graph. It's thinking. And there it is. It stopped. So, sorry, my little clock is in the way. There it is. It's the exact same picture, right? Why did it reduce to that again? Because you have inverses in here, right? Okay. All right. Let me leave it at that. As I said, this video is for Monday, so I will see you again on Tuesday. All right. Thank you, guys. I'll see you later. Be careful out there.